Hello everyone. Another very important application of the dot product is what we call vector projections. All right, so here I have some examples of some pairs of vectors, v and w, kind of oriented together, just floating around in our two-dimensional space. And I want to use these two examples to kind of help us get some sense and intuition for these vector projections. So far, when we've been working with our vectors and expressing them using components, we might write our vector v as like ai plus bj. And so that first component, or that I component, tells us how far we have to go in the horizontal or x direction. And then that second, or j component, tells us how far we have to go in the vertical direction to get to the end point of our vector. What we are essentially doing is taking our vector v and breaking it into two pieces, a horizontal piece and a vertical piece. And that's what we're going to be doing here with these vector projections. However, our horizontal and vertical pieces are no longer going to need to align with the x and y axis. Instead, the horizontal piece is going to be determined by the vector which we are trying to project onto. And so the idea is, instead of writing our vector v using components of like ai and bj, writing it in terms of those I and j basis vectors, instead we can write it in terms of this vector w and some other vector that is orthogonal or perpendicular to our vector w. So when we're trying to visualize these vector projections, we are always going to be using some right triangle to help us do that. And so we're going to consider projecting our vector v onto our vector w here. And so to set up our right triangle, we're always going to draw a perpendicular line from the vector we are projecting onto that connects to the end of the vector that we are projecting. So we are projecting onto our vector w, so we need a perpendicular line coming out of our vector w that connects to the end of our vector v, because v is the vector that we are projecting. So by introducing this perpendicular line onto our vector w, we can now more easily visualize how our vector v can be thought up as the sum of two other vectors. This is essentially what we're doing with our I and j basis vectors, but the whole thing is rotated. And so now this horizontal vector is going to be a vector that is in the same direction or parallel to our vector w. So it's just going to be some multiple of our vector w. And this second vector is going to be some perpendicular vector, a vector that is perpendicular to w. We're often most interested in this projected piece of v onto w, or this base piece right here. We'll also talk about how to find that perpendicular component, but that's usually just done doing some vector addition and subtraction. And so now this vector down here in green that was formed by creating our right triangle in our picture is the vector that we call and denote as the projection of v onto our vector w. Or another way to read that notation is it's the projection onto w of our vector v. The placement of those two vectors v and w in that notation is very important, and will give you two different things depending on their order. And one of the important properties about this vector, the projection onto w of our vector v, is that it is in the same direction as our other vector w, the vector that we are projecting v onto. And so one of the reasons why we're so interested in this quantity, the projection of our vector v onto w, is this process is very useful for solving problems related to physics. For example, imagine you're trying to drag an object up a slanted hill, and you have a handle attached to that object at some angle, and you're pulling on that handle. The object is moving up the hill, but the force you're applying to that object to move it up the hill is not necessarily in the same direction of the hill. So not all that force you're applying is actually helping and move the object up the hill. How much of that force you're applying is actually helping move the object up the hill is given by one of our projection vectors. So look at some of those examples after we finish this setup process and understand just kind of the geometry and what's going on behind the scenes for all these vector projections. Right? We know that this vector plus this vector gives us our vector v. So this vector must be equal to our vector v minus our other vector, or in other words, the orthogonal piece to our vector w that finishes off our right triangle here is going to be our vector v minus the projection onto w of our vector v. All right, so we already know the direction of this projection vector. The projection of v onto w is always going to be in the direction of that vector w, But the other thing we need to know for a vector besides its direction is its magnitude or its size. So what is the size or magnitude of the projection of V onto W? Well, we can use our right triangle to help us figure that out. And we don't even need to use the Pythagorean theorem here or find that kind of orthogonal side length. Instead, we can just do some right triangle trigonometry. Notice if we take cosine of our angle theta here, then we can relate the adjacent side in our right triangle to our hypotenuse, and our hypotenuse would be the length or magnitude of that vector V that we are projecting onto W. So just by taking cosine of our angle theta in our right triangle here, we know cosine of theta is the ratio of the adjacent side length to the hypotenuse. So that's the magnitude of the projection onto W of our vector V. That magnitude is like the adjacent side length to our angle theta in our right triangle here, and we have to divide that by the hypotenuse, which is the magnitude of V. And so now we can solve this equation for the magnitude of the projection onto W of our vector V. And that's just equal to the magnitude of V times cosine of theta. And so this is an effective formula for calculating the length of that projection vector. The length or magnitude of the projection of V onto W is just the magnitude of V times cosine of our angle theta. But maybe we don't know that angle theta, so we can't find that cosine of theta piece. There is another way to rewrite this expression that is pretty clever that will allow us to evaluate it without having to know our angle theta. And that's by recognizing that we can introduce a factor of the magnitude of W to both the numerator and the denominator of this expression. We're essentially just multiplying by a factor of 1 in a fancy way. So we didn't change the value of the expression because we just multiplied by 1. But what we did is change how it looked. And we did this intentionally because now the numerator has the product of the magnitude of our vectors with cosine of theta, the angle between them. And we can write that as the dot product between our two vectors. And so the magnitude of the projection onto W of our vector V can also be calculated using the formula V dotted with W divided by the magnitude of W. It just kind of depends on which set of information you have. That'll help you determine which formula to use, although I think in practice, we often use this dot product version of the formula more often. Just as a heads up for notation, so I've been referring to this as the magnitude of the projection of V onto W. Some other resources may refer to this as like this scalar component of our projection of V onto W, because the magnitude is just a scalar part. The actual direction of this projection vector is always going to be in the direction of W, or the direction of the vector we are projecting onto. All right, so I've had this second set of vectors up on the board this entire time, but haven't used or referenced them yet. So let's go ahead and do that. And just what I wanted to visualize with this second little scenario is what will happen if the angle between our two vectors is obtuse instead of acute. Well, the whole process is still the same and is going to work out the same. This formula is still going to apply. We just have to draw our picture a little bit differently. Remember, when we were trying to decompose our vector V into the sum of these two vectors, a vector in the direction of W added with a vector in the direction perpendicular to W, starting to draw our right triangle required us to draw a perpendicular line from our vector W that hits the end of our vector V. And well, if we try to draw a perpendicular line going from our vector W, when there's an obtuse angle between our two vectors, that's never going to happen. We're never going to have our perpendicular line actually hit our vector V, not unless we extend our vector W or actually think about heading in the direction opposite of our vector W. So we could also think of this as like our vector negative W down here. All right, so now it should be a little bit clearer with this new picture. So I've exaggerated that obtuse angle between our vector V and W. Now it should be much clearer to see that there's no way along the normal direction for W we can draw this perpendicular line that'll intersect with the end of our vector V. We have to go down here onto our vector in the opposite direction of W to draw this perpendicular line. And so now some of the little right triangle trigonometry we'd have to do would get a little bit more complicated because we have to use a complementary and reference angle. But in the end, it all still works out and we get this exact same formula. The takeaway that I want you to have from this is if the angle between our two vectors is obtuse, then when we do one of our projections, our projection is going to be onto kind of the opposite direction of that vector we are projecting onto, or it's going to be in the negative direction. So this little green vector here that's actually in the direction opposite of our vector W would be our vector that is the projection of our vector V onto our vector W. So once we find that vector using our formula over here and what we know about our vector W, we could then use the same vector addition or subtraction to find that orthogonal component to finish off our little right triangle picture. All right, so far from our analysis, we've seen that the magnitude of the projection of V onto W is equal to the dot products between V and W divided by the magnitude of W, or we could also write it as the magnitude of V times cosine of theta, although that's the less popular version. So this is just the magnitude of our projection vector, but is not actually the vector itself. If we want to create a formula that creates that projection vector, well, all we have to do is give that vector the appropriate direction. So now all we have to do to give our projection vector the appropriate direction is give it the direction of our vector W. However, we cannot just attach our scalar to a W because our W might already have some length or magnitude of its own. So instead, what we have to do is multiply our scalar with a unit vector that is in the direction of our vector W, or the vector we are projecting onto. So we want the magnitude of our projection vector to be this number that we calculated here, that is V dot W over the magnitude of W, but we need to also have the direction of W. So instead of multiplying this by just a vector W, we have to scale our vector W down into a unit vector, and we can always do that by dividing a vector by its magnitude. But after doing that, we recognize, well, we have two factors of the magnitude of W in the denominator down here. So another way to commonly rewrite this formula is V dotted W in the numerator. In the denominator, we have the magnitude of W squared, and that's multiplied by our vector W. And so the idea is this first piece is nothing but scalar factors, right? The dot product gives us a scalar. The magnitude of a vector is also a scalar. So this is our scalar, and W is just the vector that we are projecting onto. There is yet another way to write our projection of V onto W vector formula, and that's just very similar to our latest version here, where we have V dotted with W in the numerator. But instead of writing the denominator as the magnitude of W squared, we could recognize that one way to compute the magnitude of a vector squared is just dotting the vector with itself. So that denominator can also be replaced with the vector W dotted with itself. These versions of our formula for finding the vector that is the projection of V onto W are equivalent, and you might just use one over the other depending on what set of information you have. Or you might find that one version is easier to remember than the other. For instance, this one down here just has lots of dot products. V dotted with W over W dotted with W times another W. Whatever works for you.